we'll be quickly discussing the fine-tune paradigm, how it's currently being used as pretty much a standard. And then we'll see different modes of training, how to train from scratch, and what kind of changes are to be made in order to accommodate training a model from scratch, which involves using different normalization techniques and few other things. And then we'll also compare results of some of the experiments that were done on COCO dataset. We'll go through all those. So we're all familiar with the rapid progress that we have seen in the field of deep learning, especially in computer vision in the recent years. Many people attribute that to the huge amount of data that we have right now, and also the progress that we have made in the area of computations. Like we now have GPUs which can accommodate computations which are so vast that we weren't even thinking of that previously. So in a way, transfer learning has shown accelerated the progress of deep learning, and right now people even with little or no deep learning or machine learning background, they can still use some pre-trained networks and they can build their own deep learning applications, and that's mainly because of the fact that we have transfer learning and fine-tuning paradigm. So
hi, Avinash.
Yeah.
Some folks are having difficult hearing your audio. Is it possible to reposition your microphone or somehow make it louder?
Oh, let me check. Yes. Is it better now? Can anybody confirm if this sounds better?
Oh, that sounds much louder on my end.
Okay, sure. Please let me know if there is any problem with the sound or mic from my side so that I can adjust it. Cool. So it's really hard to think of an industry right now which doesn't use deep learning. Like we see automobiles, we have self-driving cars, we have, more importantly, in the field of medicine and health where deep learning is being applied. And all of these, all the progress that we have seen in the recent years, there are some very novel methods that have driven forward this rapid progress. One of those things is surely transfer learning. So transfer learning is so just to quickly say what it is, transfer learning, it's the method of using representations or information which is already learned by one trained model by another model which needs to be trained on different data. And it could be for a similar or a different task. So transfer learning uses pre-trained models, which are nothing but models which are already trained on some larger benchmark datasets like ImageNet or COCO dataset, etc. So if you have trained any model, you must be knowing that a time-taking process. Training a neural network can take anywhere between minutes and months, depending on the amount of data that we have and the target task for which we are trying to solve. So until a few years ago, due to all these kind of memory and data constraints, training a model was only possible for institutes and big tech organizations. But right now, with the help of pre-trained models, which are being readily made readily available for the entire research community by the organizations and the institutes, like everybody is now able to train the models. So using this technique, transfer learning, we can now build deep learning applications that solve several vision-related tasks much quicker than how it used to be. So, and also the good thing is in the last couple of years, transfer learning is also being, thanks to some of the progress and developments that were made in NLP, transfer learning is also being applied for language related tasks. So when Andrew Ng said a few years ago that transfer learning will be the next driver of ML commercial success, we can agree that he was spot on about it and he was totally right. So here is one example to summarize some of the training approaches that we have right now. Let's start with the one on the right end, where we have this is a train model, what we have here. And the blue block here represents the blue parts of these networks represents the trained parts. So what we have here is we have a train model, and we are going to freeze this convolution base, the block in white here. And what we're going to do is we are only going to fine tune or retrain the blue block here, which is added on top of this convolution base. So this is what we have more of a standard right now. If you have taken any of FastAI courses, this is what Jeremy shows us, right, starting right from the first lecture, where we'll be solving cats and dogs problem. We already take some pre-trained model like ResNet 50 or something. And then we are going to only fine tune the top layers, keeping the convolutional base frozen. So this is one way of doing it. And then what we do is, if the data that we have at hand is a little different, or it may not be the same as ImageNet or something, we may not get very good results with the approach on the right end. So what we do then is, instead of only fine-tuning the top layers, we're also going to unfreeze some of the layers from the convolutional base and retrain those. So this way, the model is going to use more of its parameters for retraining and fine-tuning on the new data. So this is this is going to increase the computations that are required. And coming to the left-hand part here, what we see here that the entire network is trained from scratch. So this is what we will be discussing more in this paper. So what we do is, if you have a network like ResNet 50, we are going to take the entire network, entire model, and we are going to retrain the entire model on our new data. So that's what training from scratch means. So as we can see here, the parameters that needs to be trained are going to be very huge when compared to the other two approaches that we have here. And obviously that means it's going to take a lot more time and a lot more computational resources. So if that's the case, why are we still discussing this approach? So we'll get to that soon. So in the pre-train and fine-tune paradigm, which is like you take some ResNet 50 pre-trained model and then use that to train that on your new data. The model training starts with some sort of learned weights that come from the pre-trained model. So this has become more of a standard now, especially for vision-related tasks, and also in the past few years, the same has been happening for NLP as well. So the other alternate to this is to train a model from scratch, which means we're not going to start with any pre-learned weights, but we are going to start with a model in which all the parameters are randomly initialized. So it's like you're not going to have any sort of head start which you get with pre-trained models. You'll be starting with randomly initialized weights, and then you will be starting your training from scratch. So the pre-trained models are very good at detecting high-level features. If you have read any papers on visualization of neural networks, you would have come across how the first few layers of a trained neural network are going to look for very simple patterns like edges or some sort of recurring patterns. as we go down the network, the model is going to look for more specific features that are present in the data. So these models, the pre-trained models, understand certain feature representations which can be reused. So that's what happens in the case of fine-tuned paradigm. This helps in improving the convergence and is used in state-of-the-art approaches for segmentation, object detection, etc. So if we are relying so much on these kind of pre-trained models and the pre-learned representations that they have, we should also question how good these representations are. So the feature representations learned by these pre-trained models are very domain dependent. What that means is that when you have an architecture like ResNet 50, which is pre-trained on ImageNet, whatever the representations that the model learns are very specific to that of the data which is present in ImageNet dataset. ImageNet dataset is huge, by the way, but does that mean that the pre-trained model is doing great in learning all those representations? So can we achieve what we call universal feature representations? Is it possible to do that? So when we're talking about universal representations, what we mean is we want the representations which these pre-trained models learn to be spread across a lot of data rather than just the domain dependent data that comes with pre-trained models. So some work is already done in this area where so yeah, when you're pre-training a model on much larger data set, let's say you have something like a data set which is 10 times bigger than that of ImageNet. What are the kind of improvements that the model would produce? After doing some experiments, it was noticed that just by increasing the benchmark dataset size, the target task's performance is going to scale poorly, which means just by if we keep on increasing the pre-trained dataset size, it is not really going to increase the performance of the model after a certain point. So we will be discussing the other approach, the alternate, which is to train from scratch. And the experiments for this in the paper are done on the dataset, on the COCO dataset. And they have run some trials like training a model from scratch on COCO dataset. And they have compared the results which they got with that of the fine-tune paradigm, with that of the transfer learning paradigm. So to train a model from scratch, all the parameters or the weights in the network are randomly initialized. There was some prior work also which was done in this area, which is to train models from scratch. We'll be naming a couple of those in the further slides. And the experiments that were carried out in this paper use mask RCNN as the baseline network. So, and this baseline model was trained on COCO dataset, both with by training from scratch and also with the fine-tuned paradigm. And the authors have reported the results for both these approaches. And the results that were reported prove that by training the model for sufficient number of iterations and by using some appropriate techniques, the model trained from scratch also gives comparative and close results to that of the fine-tuned model. So we'll get to the results soon. So being used to the pre-trained models, training from scratch might sound non-trivial and very time and resource consuming, which is in fact true. So we're all very used to like picking a pre-trained model and then fine-tuning that with our new data, which as I said has become more of a standard. But we are all familiar with how much research is being done in deep learning. It's happening at such a rapid pace that we can't even track of all the progresses and improvements that are happening every day. Like every day we see new research papers that are coming up and all those things. But having said that, though the novel methods and the novel architectures and all these are really necessary, it is also very much critical for us to study the existing methods in more detail, just to see if there are any loopholes in the standard procedures that we have adopted. So you must have heard about this, the problem with object detection models when someone holds some sort of a graphic and the object detection model fails to detect the objects correctly. So that's things like this would come out only when there are people who are also spending time studying the existing models in more details. Only that way we can really come up with approaches which are better than the existing ones. So some prior research was done on training models from scratch instead of using pre-trained models. To name a couple of them, NetNet and CornerNet are two of such methods. What they do is they have come up with some specialized model architectures to accommodate training models from scratch. The point of those works is that if you want to train a model from scratch, you really have to come up with something special, because what you have to do is you really have to train a model for much more iterations for a longer time, and it would take much more computational resources. So to accommodate all this, you can't simply use the existing architectures. That's what the prior work says. But the authors of this paper, Rethinking ImageNet Pre-training, they have settled with the existing baseline models, as I said, mask, RCNN. They proved the point that you don't really need any specialized architectures to show that the models trained from scratch are comparable to that of the models.
Avinash, we may have lost your audio. Is that just me?
Yeah, I cannot hear him either.
Me neither.
Oh, it looks like we lost him. Hopefully he'll be able to reconnect quickly. Hey, Avinash, welcome back. Looks like you're muted. Avinash, if you can hear this, you're still muted. All right, now you're unmuted, but we don't hear anything. Oh, sounds like your audio's back.
Yeah, I hope I'm audible now.
But it's still it's low again.
Does it keep changing?
Oh,
Okay.
that's better.
Yeah. So I was talking about the work that was done in training neural networks from scratch. So DetNet and CornerNet, to name a couple of those frameworks. What these two methods say is that in order to accommodate training models from scratch, which is very time consuming and computation resource consuming, they've come up with some specialized architectures in order to train models from scratch. But the authors of the current paper, Rethinking ImageNet Pre-training, they made a point that the frameworks that CornerNet, however, haven't reported any comparative results by coming up with specialized architectures. So the authors of this paper have instead they have used the existing baseline models. They have done all the experiments using the mask RCNN architecture by only making a couple of changes which are related to some of the techniques in the architecture. And they reported that the performances that they got are comparative to that of the fine-tuning approach. So one of the things which the authors of this paper discuss is that normalization is very critical when you have to train your models from scratch. So if models are trained from scratch without proper normalization,
Hey, sorry, everyone. It looks like we lost Avinash again.
hello?
Yep.
Hello?
Yep, we hear you.
Oh, okay. So I was saying that normalization is very critical when you're training your models from scratch.
The volume is low again.
Not sure why this keeps changing. So in this slide, we'll be talking about how normalization is critical for training models from scratch. So when you're trying to train a models from scratch, you have to get the normalization technique correct, or else it is going to produce some sort of misleading results, which might otherwise mean that training from scratch is not optimal at all. So for vision-related tasks, the training data consists of images of very high resolution. So if you have seen some data sets, like some satellite imagery data sets or something like that, you have each image which is of some few megabytes of memory, which is huge. So to accommodate that, we generally go with lesser, smaller batch sizes. The problem with that is that batch normalization is very dependent on the batch size. So if you have batch normalization in your network, and if your batch size is low, if your batch size is small, then you're not going to get the best results out of your model. So to avoid this, the authors in this paper suggest two other normalization alternates, which is one is group normalization, the other one is synchronized batch normalization. So the reason for going with group normalization is that group normalization is independent of the batch size, which means unlike batch normalization, group normalization doesn't depend on the size of the batch size. Whether the batch size is smaller or larger, it is still going to perform the same. So there's a paper on this group normalization itself, which you can refer if you want to know more about this. The other normalization technique which the authors refer in this paper is synchronized batch normalization. In synchronized batch normalization, they use multiple devices instead of a single device. And by using multiple devices and using all of those devices for training, it somehow increases the effective batch size. Like if you have like 5 devices and each device is training on data of batch size, let's say 16, the effective batch size is going to be much bigger than training on a single device. So that way you're going to have bigger batches, and the normalization is going to be affected much. So one of the main reasons why we go with the transfer learning or fine-tune approach is that the fine-tune models kind of get a head start, as the pre-trained model has already learned some low-level features, so high-level features like edges or patterns, those kind of things. So that means that the models that are trained from scratch cannot converge as fast as the fine-tune models. Though this makes fine-tuned models better, one should also consider the time and resources it takes to pre-train a model on large benchmark data set like ImageNet. So when we're talking about ImageNet is it's a huge data set which has over 1 million images, and you have organizations like Google and Facebook, which or some other big institutes who take all the time and resources and train these models. So that's a lot of pre-work which is being done. But when we are fine-tuning a model, we just assume that, okay, I only need a fewer number of images and that will do for model training. Though that is right in a way, but the model that you'll end up with is using a pre-trained model which was actually trained for many hours before. So that's something that should also be considered. And for the random initialized training to catch up and to make up for that, for all the pre-work, the model needs many training iterations. Like you have to train the model for much longer time than that of the fine-tuned approach. So here, we have an image here on left. It represents the total number of training samples which are seen in both cases, which is training from scratch and as well as using the fine-tune paradigm. As we can see here, we have the gray and the purple color kind of thing for training from scratch. What we see here is when you have a fine-tuned model, as we can see here, the total number of images that the model sees in the case of transfer learning approach is 131 million, which includes both the pre-trained benchmark dataset and the COCO dataset on which the model is retrained. But if the same model is being trained from scratch, then all the data that the model sees is only 8.6 millions. So there is such huge gap between the number of instances that the model which is fine-tuned takes than that of model which is trained from scratch. So what we see here is images, instances, and pixels. These three are for different kind of tasks that we have. If you're talking about have images like images of cats and images of dogs. If you are talking about object detection, every image might have some n number of instances. So that's what instances here refers to. And if the target task is something like image segmentation, everything happens at the level of pixels. So as we see here, only when the target task works at the level of pixels that the amount of training data or samples is almost the same for both fine-tuned and training from scratch paradigm. But other than that, we can see that the training from scratch approach needs much fewer examples or data when compared to the transfer learning approach. So coming to the experimental settings, the architecture and the hypermethods used are mentioned here. So as I mentioned before, the authors have used mask RCNN with ResNet and ResNext architectures as the baseline. Group normalization or synchronized batch normalization are used for normalization. And the model is trained with an initial learning rate of 0.02, and it's reduced by 10 times in the last iterations of last 60K to 20K iterations. And there is no test time augmentation that was done, though in some of the results reports, the authors have also mentioned have also showed results with test time augmentation. And the authors have they used 8 GPUs for training. As mentioned before, synchronized normalization uses more devices. That way, it increases the effective batch size. So by training model on Cocoa dataset with these settings, Cocoa dataset has 118K. If they have done the training on different amounts of data. So one of the trial is training a model from scratch on 118,000 training and training images and 5,000 validation images. So the authors have seen that the model that was trained from scratch was able to give very comparative accuracy results with that of the pre-trained model or the fine-tuned model. And they have reported this for both object detection and image segmentation tasks. So as we see in the plot here, the plot on the left was trained with ResNet 101 and group normalization, whereas the one on right is trained with ResNet 50 and synchronized batch normalization. The spikes that we see here, those are just some other results that were overlapped and shown in the same plot instead of using 5 different plots. So we see that when fine-tuning, the pre-training model has some sort of a head start. Here we can see that the gray curve starts with the bounding box average precision score of around 20. So whereas the model which is trained from scratch starts somewhere at 5. So there's a huge gap here, which means the fine-tuned model has some sort of head start, and that's very expected because the pre-trained model has already been trained on some huge data set, which is why it starts with much better results. But the interesting thing to notice is that after some certain number of iterations, we see that the average precision score for both the fine-tuned and training from scratch approaches, they somehow meet each other. It's more like they both start giving the same sort of results. So this is one of the comparisons. And so the authors also tried to make some enhancements to their baseline model. So the baseline model that the authors used is mask RCNN. What they did is they tried to do scale augmentation during training, and they reported that they got better results. And they also used something called cascade RCNN, and they added test time augmentation as well. And they showed that this further improved the results. So with test time augmentation, model trained from scratch gives slightly better results than that of the fine-tuned models. We'll see the plots here. So as we can see here, I hope it's clearly visible. Sorry. So we have here ResNet 50 on left and ResNet 101 on right. What we see is in different kind of settings, like here in the second column of plots that we have, the authors have showed how the using training augmentation is going to impact. What we see here is the first one, the first rectangular box here represents training from scratch, whereas the next represents training from using a fine-tuned model. We see that the accuracies or the scores are almost the same. And an even interesting result is this final one here, where cascade mask CNN is used along with train and test augmentation. The score that was reported for training from scratch is 48.6, whereas the one that was reported for fine-tuning approach is 48.3. It's only, it might look like it's
Hi, Avinash. We lost your audio again. Still there? All right, we are waiting for Avinash to rejoin. Anyone want to chime in with any questions or comments or anything before, or conversation while we're waiting?
hello.
Yep.
I'm terribly sorry. I have some bad internet connection at the moment.
Your audio is very choppy right now.
Is it better now?
Yeah, that's better.
Okay, thank you. I hope I was here until I was showing you all this plot. Yeah, so the final experiment or the next experiment was to try with different amount of training data. So the COCO dataset has more than 100,000 training examples. So the first interesting result from this paper is that we can get comparable results even with models trained from scratch that we have seen in the previous plots. Now, the other rather surprising discovery is that even when the data is less, training from scratch can still produce close results to that of the fine-tuned models. So here in in this in this experiment, uh, the authors have they try to train a model using only a subset of COCO dataset. Like when working only with 1/3 of the whole COCO training data, which is like 35,000 images, experiments show that the fine-tune approach starts overfitting. And that is an interesting observation because that shows that ImageNet pre-training doesn't automatically help reduce overfitting. But despite less data, training from scratch still catches up with fine-tuned approach. And another experiment was done with only 1/10 of training data, which is close to 10K images. Now think about it. Initially, the authors have trained the model from scratch using 118K images, and they have shown that the final accuracy or the performance results catch up with that of the fine-tuned approach. And now the data has come down to 10K images, 118K images to 10K images. And even now, they have noticed that training from scratch produces comparative results with that of the fine-tuned approach. So here again are some plots. So on the left, we see that the pre-train and fine-tune approach, the model starts to overfit after some iterations. We see that after a certain point, we see that training further is going to decrease the model performance, and that's seen in fine-tune approach. Uh, we see in the plots on the middle and right, we see that in both these cases, the training from scratch approach catches up with that of the fine-tuned model. So that's an interesting observation. So we have now, starting with 118K images, we have now come down to only 10K images. So what happens if we further decrease the data, reduce the data? So the authors have also done that where they trained the model using the same settings, but using only 1,000 training images from COCO data set. So when only 1,000 images are used, training from scratch still converges, but it happens slowly. But this is kind of the threshold point where the model starts producing burst results. Like where with 1K images, the fine-tuned model reports score of 9.9 position, whereas training from scratch reports 3.5, which is far lesser than that of training from training. So this is kind of the threshold. Like when you bring down the data of COCO dataset to one by 100th part of the original data, only then the authors have noticed that training from scratch hasn't done well. So these are all the experiments that were carried out in this paper. So this is the summary of what all we discussed so far. So Hello.
Yep.
I'm sorry. So I'll quickly conclude this summary so that we can have Q&A. So I was saying that the paper nowhere claims that the fine-tune approach is not the right way of doing things. What I really felt, what made me really interested in this paper is that this is a study on the alternate approach to transfer learning, which has been more of a method that has been left out due to the time and resource constraints that it comes with. But if time and memory are not the constraints, then I think methods like this have to be studied and tried out, so that even if they report some sort of improvements in the performances, they can make a difference, because deep learning is currently being used in many critical areas, like which even includes health and medical industries. So so that's all about this paper. I'm open for any questions now, and my sincere apologies for all the interruptions that that you all have to bear.
All right. If you have a question for Avinash, feel free to unmute and ask it, or submit it via the chat. Any takers on questions? Avinash, I'm not so sure if I saw it, but was there any graphs provided on the computational aspects of this?
No, Sam. They haven't shown any plots on the computational aspects, but what they
I can't hear you actually.
Can you hear me now?
Yeah, that's fine. Thanks.
So the authors, they haven't shown any plots from the computational perspective, but what they have mentioned in the paper upfront is that this approach, which is training from scratch, it is computationally intensive and when compared to the fine-tuned approach. They did say that the model has to be trained for more number of epochs, which means it is going to take longer time and much more resources than the transfer learning approach. But no, they didn't really have any plots for that aspect.
Okay.
So as I said, what's really striking about this paper is that nobody would really consider training from scratch as an option when they can go with the transfer learning approach. But we have seen that in an effort to come up with novel and new methods, we should not overlook looking in depth into the existing methods, because you never know what loophole or flaws exist in these kind of existing methods. Even if trying out something new with methods is going to produce slightly better results, maybe that would make some difference in industries like automobiles or health. So that's what really interested me in this paper, like taking time and studying an approach like this, which is otherwise left out for time and computational constraints.
Okay, awesome. Well, thanks so much for taking the time to present this. And thanks, Matt, if you're still there, for hosting this meetup. I've kind of jumped in because you're traveling, Matt's traveling, but if you're still on, you feel free to close us out. Otherwise, have a great day, everyone.
Thank you, Sam.
Hey, thank you so much for presenting. Yeah, I really appreciate it. Yeah, it was a really wonderful presentation. And thank you, Sam, for jumping in a couple of times. I'm sorry that the audio kept cutting out, but it seemed to work out at the end.
Yeah, sorry about the audio again, but thank you all for.
Thanks, everyone.
Yeah, thank you all. Thanks, Matt. Thanks, Sam.
Bye-bye.
Bye. Have a good day.